Okay, let's start. Today we are going to talk about the characterization of the invertible matrix. In the previous lecture, we were talking about the invertible matrix, right? So today we are going to talk about the characterization of the invertible matrix. Then here's the theorem. So the name of this theorem is called the invertible matrix theorem. Actually, this theorem is the most important theorem during the chapter 1 and chapter 2 because this theorem is provide a review of the most of the concept introduced in chapter 1, so in related to the system of the n linear equation in n unknown. So this case means something like the ax equals b when A is a matrix n by n matrix. So until this week, we have talked about the several kinds of property of the related to the this matrix A, right? So we have discussed what is a span, what is the onto, what is a one-to-one mapping, what is a uniqueness, what is the existence of the solution, something like that. But all of the concepts are related to the property of solution ax equals b. So in this theorem, in this invertible matrix theorem, we will summarize how these concepts are related to each other. Then how can we use these kinds of the theorem in a unified in a unified theorem? Okay, so let me summarize this theorem in Korean first. 네, 지금 이제 저희가 다섯 번째 주죠. 지금 다섯 번째 주까지 오시면서 AX equals B라는 어떤 시스템, 리니어 시스템의 솔루션을 어떻게 찾을까? 그리고 이 솔루션들의 어떤 프로퍼티들이 있을까? 그리고 이 시스템 자체에 어떤 프로퍼티들이 있을까를 각각 어떤 파트별로 배워왔습니다. 그쵸? 이제 뭐 리니어 인디펜던스라는 개념부터 시작해서 뭐 다양하게, 그쵸? 뭐 이거를 뭐 로 리덕션을 어떻게 푸는지, 뭐 이게 온투가 뭔지, 원투원이 매핑이 뭔지, 사실 다양한 컨셉들과 시어럼들을 배워왔는데, 사실 이게 사실 다들 각각은 알겠지만 연결이 잘 안 되실 거예요. 그쵸? 왜냐하면 그럴 수밖에 없습니다. 이제 이 인버터블 매트릭스 시어럼을 이제 오늘 배우고 나면은 이제 그 시어럼들이 각각 하나의 시어럼으로 이제 연결이 될 거예요. 그래서 걔네들이 각각을 만족하는 것들이 다른 시어럼들을 어떻게 만족을 하는지를 오늘 이제 배울 건데, 이제 이걸 통해서 저희가 이 단일 시어럼을 통해서 이 ax equals b를 해석을 하기 위한 이제 단일 시어럼이 생긴다고 보시면 됩니다. 네, 그래서 이제 여기까지 오늘은 수고하셨고, 이제 오늘은 지금까지 배웠던 저희가 슬라이 매터리얼들을 쭉 펼쳐 놓으시고 각각의 매핑되는 이 시어럼들이 어떻게 우리가 배웠던 것에 연결되는지를 한번 매핑해 보면서 이제 마지막 저희가 지금까지 얘기했던 것들이 과연 하나의 시어럼을 어떻게 연결되는지를 오늘 보시게 될 겁니다. 네, 그러면 오늘 이제 강의를 시작하겠습니다. Okay, before starting the today's lecture, I suggest you to prepare our previous material that containing the several kinds of theorem. Then today we will see how these kinds of the theorems are related to and can be mapped into the single theorem. Okay, so let's start. Okay, here is a theorem. Okay, let's discuss on the matrix A with the size of the n by n square matrix. N by n square matrix, something like this. Then following statement are equivalent, or the statement are either or true or false. What does it mean? It means that those kinds of the theorem from A to I holds these theorems are equivalent. So if one of these theorems is satisfied, then all remaining theorems are also satisfied. Otherwise, if one of these theorems is not satisfied, then whole remaining theorem is also not satisfied. Okay, so this is the general idea. So what does it mean? If we know one of these, if we see the arbitrary matrix that or if we know the arbitrary matrix A is satisfied one of this theorem, then we can infer the one of the another theorems that also satisfy. So it means that we will analyze this matrix A using this kind of the theorem. Okay, so okay, let's start. Okay, there are several kinds of the statement. First of all, A is the invertible matrix. What is the invertible matrix? If the matrix A is invertible, there exists A inverse, right? Then what's that? A times A inverse is equal to A inverse times A is equal to I. So statement A is meaning that there is the inverse A, right? Another statement is A is a row equivalent to the n by n identity matrix. What does it mean? Okay, let's say we have a arbitrary matrix A, then by using some kinds of the row reduction algorithm, we can convert the original matrix A into the reduced echelon form of the matrix A, right? So this statement means that A is row equivalent to the n by n identity matrix, means this reduced echelon form of the matrix A is the n by n identity matrix. Looks like this. Okay. Then what is the next statement? A has the nth pivot position. What is the meaning of the pivot position? Okay, if we have the matrix A, something like this. N pivot position means because the size of the matrix A is the n by n, then pivot position should be here, right? So pivot position, because there is the n pivot position, right? Another statement is that the equation AX equals B. This is a homogeneous system, right? Homogeneous system has the only trivial solution. When does it happen? X is equal to 0 vector, right? So their trivial solution means there's only one solution as a vector x as a 0. Okay, so this is the statement. The columns of vector A form the linear independence. Linearly independence. What does it mean? What is the columns of vector matrix A? Okay, let's say matrix A consists of the n column vector, something like that, and the linear independence means. Okay, before we see the linear independence, let's go back to the lecture 3.1. No, what was that? Yeah, lecture 4.1. There was a linear independence, right? So when is the linearly independence? Given the set of the vector v1 through the vp had can be represented something like this with the coefficient x1 through the xp. This is a vector equation, right? So if this vector equation has only trivial solution, that it called the linear independence, right? Then what is the trivial solution of this vector equation? What is that? 0 vector, right? So it means that if this equation, this vector equation have the zero vector as a solution, it called the linear independence, right? So in other words, C1 A1 plus Cn An equals 0, where when C1 through the Cn or 0. In this case, this is called the linear. These vectors are linear independent, right? Let's move on to the next statement. The linear transformation x to the ax is 1-to-1. What was that? If the input space x and output space a times x, something like this, what is on-to-1 means? Each input pixels mapped to the only single output, something like that. So this is called the one-to-one, right? What is the equation? What is the next statement? The equation ax equals b has at least one solution for each vector b in Rn space. Rn space. So at least one solution means exact one solution, or infinitely many solution, right? Right. Then the next one is the columns of the A span the Rn space. Rn space. What is the span? What is the span? The linear combination of the vector, like this, right? So this is the span that have the different parameter C1 through the Cn. So the span of those column vector, the span of the columns of the matrix A means the every possible linear combination of the vector A1 through the An. Okay, so the span Rn means this span is equal to the Rn space itself. Okay. Another thing is that the linear transformation x to the ax map Rn space onto Rn space. What does that? What does it mean? X is the input vector and A transpose X is the output vector, and here's the mapping function, something like that. If this output of the AX or range of the vector X, this is the output, right? So when the output of the transformation A has output of the A times X is equal to the Rn space, then it is called the onto, right? Right. And one more thing. So there is a m by m matrix C such that C times A is equal to I, and there is a matrix B such that A times D is equal to I, right? Then finally, A transpose is an invertible matrix. Okay. Okay. So here are theorem. So okay, from now on, let's prove why those kinds of the concept or the statement are related to each other. Okay, so before move on, if you want to understand what is the row equivalent, what is the pivot concept, what is the trivial solution, what is the span, what is onto or one-to-one, something like that, please go back to our previous lecture, because you can access our previous lecture on our YouTube channel. So please go back to the previous lecture and understand what is the meaning. Then from now on, let's prove this theorem. Okay. Before starting, we want to find some kind of a circle, something like this. It means that if the statement A is satisfied, then remaining statements are also satisfied. So by finding some kind of chain, something like this, then we can prove the every sub theorem. Every sub theorems link with each other. Okay, so let's start. First of all, statement A is true. If the statement A true, A inverse works for the C in I. What do you mean? If this theorem, A is an invertible matrix, then C should be what? In this equation, C should be A inverse, right? So there is the n by n matrix C as A inverse, right? So we can say that statement A implied J, right? So okay, first we find the link here, right? And then if J is true, this is true. Why? This is J, right? There is the n by n matrix C such that, something like that, and T is true. Where's that? T. The equation has only the trivial solution. Why? Why? Because here A inverse A is equal to I, so it means that by multiplying the A inverse on the left hand side here and right hand side, something like that, then it should be identity matrix. So it means that X is just 0, right? So the same, right? So it means that J implied this statement, right? So we find the link J to the T, right? What about D to the C? T is here, right? And C is here. So the equation AX equals 0 has only the trivial solution. Then A has the n pivot position. Why? Why? So the two yeah, we can say like that. Okay, so if the equation AX equals 0 has the only trivial solution, we can say that there is no free variable. Do you remember what is a free variable, right? If there are free variable, there are infinite domain solution as bearing the free variable, right? But because there is only the trivial solution, so it means that there is no free variable, right? So what does it mean? If there is no free variable, every column should contain the pivot position, right? Something like this, right? So it means that A should have the n pivot position because there are n row, right? So it means that the statement T implies the statement C, right? Okay, we find the from T to the C. Okay. Okay, let's move on to the next. From C to the D, C to the B. If A has the n pivot position and matrix A is a row equivalent to the n by n identity matrix. N by n identity matrix. What does it mean? Okay, let's say there matrix A has an n pivot position, something like this, right? Then what does it mean? This matrix A can be row reduced form, something like row reduced form, something like this, right? But interestingly, because we already know that their n pivot position, right? So n pivot position should remain in the reduced echelon form. Then what is the value in the pivot position in the reduced echelon form? 1, right? And the remaining part are 0. That, right? Then what is that? This is the identity matrix, right? So it means that if A has an ampere position, then A can be low reduced to the n by n identity matrix, right? So this statement true, right? Then what about B to the A? B to the A. If A is low equivalent to the n by m identification, then A is the invertible matrix. Why? Why? To understand this, we have to go back to the lecture 5.2. 5.2. Here, this theorem. In this theorem, on n by n matrix A is invertible if and only if the matrix A is a low equivalent to the In. Right? So this statement, this relationship are true, right? By the way, in the last week, I mentioned what is the meaning of the if and only if, right? What is the if and only if? This relationship are true, and this relationship are also true. In case this poor relationship and this backward relationship are also true. So in this case, this is called the if and only if case. Okay. So what does it mean? So A is invertible means A is a low equivalent to the In, or A is low equivalent to the In, and A is invertible. Okay. So this is the if and only if, right? Okay, let's go back to our proof. Okay, now we proved P to the A is true. Okay, so finally we make the one circle, something like this, right? Okay, let's move on. Okay, let's find the relationship from statement A to the K. A means the matrix A is the invertible matrix, right? Then K, there is an n by n matrix D, something like that, right? We already know D is the inverse matrix, something like this, right? It means that inverse A times inverse A is equal to I, something like that. So this is also true, right? Then yeah, A to the K, right? Then what about the K and G? K and G. K is here, G is here. There's the matrix D, something like this. Then equation AX equals B has a at least one solution. At least one solution. Why? 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 K, we have a K, we have G, right? So to see this one, we need some kind of the technique, okay? Let's say like that. The matrix D can be represented something like the T1 through the Tn, right? As a vector form, right? Column vectors, right? And what is identity matrix? Identity matrix, something like the element matrix vector 1 through the element vectors 2, right? Then this one, A times D, this one, this is equivalent to the, okay, let's write here. It's equivalent to the AD1 is equal to E1, right? AD2 equals DE2, something like ATN to the ED, right? So it means that each of these equations has at least one solution, right? Because the to prove this one, we need one more theorem here. So this is the theorem in our lecture 3.1, right? 3.1. There was the 4 sub-theorem, and they are all equivalent, logically equivalent, like the today's theorem. In here, there was the column. Yeah, here, let's see it here. The columns of the matrix A span the RM space, then it has a solution, right? So if we go back to the today's proof, this one means the column vector. How can we tell? Because the column vectors, yeah, let's see this one. This one equation has at least one solution, right? Because A is not. Okay, let's see that. Because this term is it's not a zero, right? So it means that this equation has at least one solution, right? Because this is not a non-trivial, non-homogeneous case, right? So it means that those equations has the it means that we can say that the columns of matrix A span R3 space, Rn space, right? So it means that from this statement here, we can conclude that the equation Ax equals B has just one solution, at least one solution, right? So it means that K to the G is satisfied. Okay, so we find the G to the A, A true. Okay, so we find another circle here. There was one circle and there is another circle, and the A is related to this one and this one. So this whole statement are related to each other, right? Okay, so let's move on to the GHI. They are all equivalent. Why? Why GHI are whole equivalent? To understand this, we need to go back to the previous lecture, 3 times 1. So in 3 times 1, vector has at least one solution, then columns of A is the span Rn space from this one and this one, right? So this is true, and the linear transformation x to the ax map to the onto. So what is the concept of the onto? We have to go back to the lecture 4.3 here. So this statement are true when the columns of A span the Rn space. So column space span the Rn space, then this transformation map Rn space onto Rn space. So these three kinds of the statements are whole equivalent. So it means that G, H, I are linked and have the circle. So G and G the same, so they are whole related, right? And what is the remaining things? EFI, right? EFI. Okay. So first of all, T statement T is linked to the EF. EF. T, this one has the link to EF. Why? Why? If A has only a trivial solution, then to understand this, we need to go back to the lecture 3.5. No, 3.2, what was that? 4.1, right? So 4.1, okay? So this equation has only trivial solution that columns of A form the linear independent set. So this is the definition of the linearly independent. So because they has only a trivial solution, x as a x as a 0, then this is the linear independence, right? So from this one we can conclude the from statement T to the E is true. Okay. What about this? What was the one-to-one? We need to go back to the 4.3. Lecture 4.3, there was the statement something like that. T is one-to-one if the columns of A is linearly independent, right? So T to the F is also true. Okay. So T, E, F are all equivalent, right? So and T was already have circle something like this. So E and F are also related to also contained in the circle, in the previous circle, right? Then yeah, finally statement I. What is that? A transpose is an invertible matrix if A is an invertible matrix. To see this one, we need to go back to the previous lecture in the invertible matrix theorem here, right? So the inverse of matrix A transpose exists. Then the transpose of invertible matrix the inverse of the A transpose is the transpose of the inverse matrix. So because the inverse of matrix exists, so inverse of the A transpose is also exists. So this A to I, this A to I is also true, and I to A is also true. So they have the circle, something like that. We already know the statement A have circle here, right? To summarize, so those every statements are whole related and they are whole logical equivalent. So these statements are either or true or false. Okay. This theorem is really important and it will help us to understand what was the previous theorem and how they can be related to each other. So please try to understand the whole statement yourself and try to prove this kind of the theorem by hand. Okay, so let's move on. Okay, here's the example. Okay, use the invertible matrix theorem to decide the matrix A is invertible. What's that? This is the theorem A, right? A, right? So first of all, to understand the A is the invertible or not, we can row reduce this original matrix A. Original matrix A, this one, as a reduced echelon form or just echelon form. Okay, how can we do that? We can remove this part by using this one. So we can make it this one. Then what next? We have to remove this one. So we make like this. Okay, so this is the echelon form, right? Right. From this, we can find that the A matrix A has the 3 pivot position. Here, 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 right? So what does it mean? So it is a statement C here. A has an n pivot position because this is a 3 by 3 matrix, right? So it means that this satisfies the statement C. So statement C and statement A are related. So we can conclude the matrix A is invertible from this one, right? So this is the one example that used the invertible matrix theorem. Okay. Okay. So there are one more fact or there's one more property. Let's say there is the two matrix, the two square matrix A and B, and if A times B is the identity matrix, then A and B are both invertible with the B is equal to A inverse and A is equal to B inverse. Okay. Okay. So let's prove something like that. If A B equals I, then here JK, then C and T is the inverse matrix, right? Right? From the relationship between the statement J and K and I, right? So C and D are inverse of the matrix A, right? So from this statement, first of all, there exists inverse of matrix and inverse of B matrix, right? So there exists. Then from the AB is equal to I, by multiplying the inverse of A on the left hand side and right hand side, something like this. This is the just identity matrix. Then P, this I, right? So from this one, P is equal to A inverse, just right. Then another thing is that AB is equal to 1. We can multiply the inverse P inverse on here, something like this. Then this is identity matrix. Then A is the B inverse. Okay. So this is some proof. Okay. So yeah, here's one more concept. There is a notification that the invertible matrix theorem that we discussed today only apply to the square matrix, something like the n by m square matrix. This theorem cannot be applied to the general case, something like m by n, where m is not equal to n. Then we cannot use this invertible matrix theorem. For example, if the columns of the 4 by 3 matrix are linearly independent, we cannot use the invertible matrix theorem to conclude anything about the existence or non-existence of a solution of the equation of the A is equals B. So please be careful. The invertible matrix theorem is only defined on the n by n square matrix. Okay. Here is one more concept. Invertible linear transformation. What is that? Okay, so we already know the matrix multiplication corresponded to the composition of the linear transformation. What does it mean? Okay, let's say we have some space, input space, something like this, and have some transformation A, then we can get the A transformation, A transpose A times vector X, right? Then if there is one more transformation P, we can also get the P times A transpose, something like that. Then matrix multiplication from X to the P A X, then there exists a transformation, a linear transformation A times B. That is same to this one, right? So this is the matrix multiplication property, right? So in this case, in here, the matrix A, if when matrix A is invertible, it means that there exists the inverse matrix A, right? Then the equation A inverse, this is A inverse, okay? A inverse times AX is equal to X can be viewed the statement of the linear transformation. So what does it mean? Okay, so let's start from the vector X, and then by multiplying some kind of transformation A, then we can get the AX. Then if we multiply this point to A transpose, A inverse, then it will be go back to the original one, right? Why? Because from this one we can multiply A inverse AX, right? So because this is identity matrix, right? So it will be the vector X itself. So it will be go back to the original point. Okay. So this is the concept of the invertible linear transformation. Then this concept will be extended to the general case, something like that. So okay, there is a linear transformation T, Rn to the Rn space is called the invertible if the S another transformation S Rn to the Rn such that STX is equal to X, TSX is equal to X. So in the geometric relationship, there is the input X. By using the transformation T, we can get the new vector, something like that. And by using the transformation S here, we can get another vector S, something like that, right? So yeah, this is that. Let's notate something like that. So right. So if these 2 points is equal to each other, then this transformation S is the inverse transformation of the transformation T. Then, in other words, this transformation T is invertible and has the inverse transformation as S. Otherwise, we can exchange this T to the S and S to the T. So it says by this one. So it means that the transformation Rn to the Rn is a linear transformation, and matrix A as the standard matrix, right? So standard matrix was just the matrix form of this transformation, right? Then transformation T is invertible if and only if the A is the inverse matrix, invertible matrix. This is very intuitive, right? This is very intuitive. Because transformation X is just the A transformation, right? So it means that if there exists the inverse matrix O matrix A, then there is another transformation T, inverse inverse transformation. So something like this. So this is related to each other. Okay. In that case, the linear transformation S, this one can be represented something like that. So what does it mean? Okay, so inverse A should X itself, right? Then we already know that this is the transformation X, right? And then from this statement, represent something like that. Says Tx is the inverse of the X, right? Right? Why? Because this statement can make this one, right? So this transformation S is the inverse transformation of the transformation T. Then it means that the how can I represent this? Yeah, transformation X is the A transpose X, so it means that S transpose X is the inverse of matrix A. Okay, so this is the inverse transformation X. Sx is equal to A inverse X, and this is the unique function. Okay, so or I can prove something like this. Okay, then let's say S transformation X is equal to S AX, right? Then inverse AX is equal to X, right? So from here we can conclude this statement are true. Okay, so this is a proof of this theorem. Okay, this is the end of the today's lecture. As I mentioned in the first, this invertible matrix theorem is one of the most important theorem in this chapter. So please try to understand what is the meaning of each terminology, and then try to prove those kinds of sub theorem. Okay, then if you can understand this all kinds of the theorem and what is the meaning of this theorem and how they relate to each other, then you can understand any kind of the Ax equals B case when A is the square matrix. Okay, so it will be just the summarization of the concept that we will learn until today's lecture. Okay, thank you very much. Let's see the next week.